Right, look at we can determine these loss impedances in a transformer practically. So the values of the loss impedances in a real transformer model can be determined through practical experimentation that involves 1. Doing an open circuit test, measure the power input, primary and secondary terminal voltages and the primary current. We take those readings and then we do a short circuit test measuring the power input, the primary terminal voltage and the primary current. A note there, care is needed when performing the short circuit test to short circuit on the secondary to make sure you don't go over the rated VA of the transformer. Okay? So what we're going to do is have a look at how that works with an example of an imaginary transformer and some given readings, so you can see how that works. Then we're going to try it out on the single phase transformer over there with a given load. So we'll find what these parameters are, use the simplified model to determine what currents and voltages we get when it's loaded with a certain value resistor, and then we'll plug it all in and see how close we are. Hopefully we'll get all that done today. If not, we'll just finish it off next week. All right? So, again, I apologise for the poor board, but it's what I've got to work with. So the open circuit test, the only thing we have connected to the 8 volt meter, which is high impedance anyway, the watt meter will provide us with the power loss in the core. So we've got a watt meter in there that will tell us how much power the core is using. The apparent power supplied by the source you can get from multiplying the primary current and the primary voltage. So you can get SM. Reactive power absorbed by the core can come through calculation, because if we know the power and we know the volt amps, we can find QM. Then we can calculate a resistance representing the core loss from E primary squared over the power. So using one of the power formulas rearranged. The magnetising reactance XM can be found by EP squared over QM, and the turns ratio can be obtained from EP over primary over E secondary. And that's from the readings that we get on those meters. The short circuit test, again we have a watt meter, an ammeter and a voltmeter in the primary side. We short circuit the secondary and use a much lower than normal voltage to take readings of watts, current and voltage. And the full transformer impedance referred to the primary, because what we've got connected here to this power supply is the resistance of the secondary winding and the resistance of the secondary winding and the resistance of the primary winding. Yeah? So therefore, you can find that. The total impedance is the short circuit voltage divided by the short circuit current. Transformer resistance, referred to the primary, is power short circuit divided by I squared short circuit. And then lastly, we can get the leakage reactance using Pythagoras theorem with the triangle, as we've always done. Okay? What we then have is a model where all the loss impedances are combined together as one resistance and one inductance. So we can then use that, take this short out, add a load in, work out values, transfer them back, to the secondary and model what that transformer is going to do for load on it. Okay? So that's a problem that uses that. A short circuit and open circuit test is carried out on a 500 kVA transformer. It's 69 kilovolts down to 4.16 kilovolts at 60 hertz. Following results. Open circuit results: primary voltage 69 kV, power drawn 5 kilowatts, primary current 0.15 of an amp. That gives you some idea of how negligible that current is once you load the transformer up. Yeah, because that primary current ain't going to be 0.15 of an amp when you fully load it. And E secondary 4160 volts. Okay. And then the short circuit tests, primary voltage 2600, so you can see a much lower voltage applied to keep the secondary current down. Power short circuit is 2400, and the short circuit current in the primary 4 amps. Use this data to produce a simplified model of the transformer and find values representing the core resistance, the magnetising reactance, the voltage at the secondary terminals with the load connected, the active power delivered to the per resistance of 50 ohms, power supplied by the source, and the efficiency of the transformer under these conditions. So once we've done that, we can do all of this stuff. Yeah. So, on load, the open circuit scenario. Five kilowatts. How can we get SM? What measured values do we need to use? Sorry? EP, IP. (69) times 10 to the 3 multiplied by 0.15 equals 10,350. Units, Mike? S, that is. Amp power. Yeah, in power P's in watts. S is VA, volt amperes. Alright? What can we find now? Now we know PM and SM. Q. How do we do that, James?
QM equals whatever equals SS.
Yep. That is root 10,350 squared minus 5 kilowatts. That was the reading, wasn't it? Squared equals. We get 9,062 var. Yep. Which of the two components is representing the dissipation of 5 kilowatts? What type of component dissipates real power? The resistive power. Yep. The resistance. So that's the. If we want to find what the resistor is representing that, which is called RC, what do we need to do? Yeah, you could use the power of the current or the nominal voltage. Yeah, so you can use it's one of the over PM. It's the formula voltage squared over R for power rearranged. A lot of ohms. What, that? No, sorry, there isn't. That's turned as if by magic. You zapped it, so.
Well, it's 7 o'clock.
Yeah, might be on time. That's. I got 952 kiloohms. Do we agree with that? Yeah. So that resistor representing that 5 kilowatts is 952,000 ohms. And then XC, the inductor, representing the magnetizing current of the core, that's going to be EP squared again over what? QM. Yeah, because we're interested in the out of phase component. That's 69,000 squared over, was it 9,000 and something, wasn't it? 9062. Somewhere around about a little bit over half, but you got 525k. Yep. And the last thing we can find from the open circuit test is transformer ratio. I is equal to EP over ES equals 69,000 divided by 4160 equals, and I got 16.6. Just check it because I have been known to get stuff wrong, as you all well know. Yeah. So what we've effectively done there, so we've got an open circuit model of this transformer. It's got 900 and some odd K, 952K resistor, RC, and an XC of 525K. Going into our ideal transformer, but at this point is open circuit. So that would model that transformer's open circuit behaviour. Yeah.
For your winding and your all the two that we're talking about here at the top, that's
Yeah.
incorporated into one of the
It's going to be, yeah. Remember when we do on-load with the simplified model, we ignore those components anyway. Yeah, just giving you an idea so you can see where the 5 kilowatts come from. Yeah, when it's open circuit. So anyone who thinks when they got a power supply for a laptop or something plugged in, but it's not plugged into the laptop, it's not drawing any current, think again. Might not be drawing very much, but it's drawing some. Yeah. So that's the open circuit situation. The on-load situation can be modelled as finding one value RP and one inductor XP in the primary. They're effectively the resistance of the primary and secondary windings added together, and the inductance of the primary and secondary windings added together, and our load can go in there. But what we're saying with this test, is we're short-circuiting that. Yeah. So we're doing a short-circuit test. Yeah. So if that's 0 ohms, A squared times 0 is 0. So effectively we're saying that's doing nothing to the rest of the circuit except allowing current to flow. This is the short circuit test. And the question gave you EP 2600 volts, power short circuit 2400 watts, and I short circuit 4 amps. So what can we find on that? Think about what we could say this is if we combined the value of both those two components briefly. Yeah. Yeah. So in that green box is ZP. What can we say that's equal to? How can we calculate that from the information already given? Yeah. Well, yeah. dP over ISC. 2,600 over 4 amps. $650 ohms. Alright. It's got some angle associated with it, but we have got no way of calculating at the moment. Yeah? It's the impedance, remember? It's the two components combined together. What else can we calculate from the information given? We've used the voltage and the current. For some reason we got the power. There's a clue. Yeah, because RP, the resistance on its own, is the only thing that's going to dissipate real power. So all of that 2,400 watts must be being dissipated in the windings of that transformer under those conditions. And then once you've got the you can work the triangle then, can't you? Once you've got two legs of any two legs of them triangles, you can find the third one. So we can find RP from P short circuit over I squared, ISC squared. Again, that's the P is equal to I squared R formula rearranged. 2,400 over 4 equals 150 ohms. So what we've got then now is two legs of our impedance triangle. We've got Z and we've got R. So now we can find X. P. Yep. XP is equal to root ZP squared minus P RP, sorry, squared. That's root of 650 squared minus 150 squared. And I got 632 ohms. Okay. So now we've got the armory we need to have a model that will allow us to analyse what happens when we put a particular load on that transformer. Because we've got a transformer model now that's like this. E.g. a value for that resistance, a value for that inductance. We can connect any load. That's ZL dash there. And these are going to be effectively the ES terminals, the secondary terminals at that point there. It's ES dash as it stands. Let's transfer to the secondary. Right, and we know we've got 69 kV there. The value of those two components were 150 ohms and 632 ohms. So, if the real ZL is equal to 50 ohms, ZL dash is like squared ZL 16.6 one at I. What we got? .8 kiloohms. Alright? Now, just pause.